Testing.
Yeah, I can hear you.
All right, thanks. So we've been doing things in time and frequency or S domain. Oops. And looking at functions of t and finding this relationship, right? But then we also learned that there was another way to find this. By taking the Laplace transform first. And then just multiplying instead of convolving, and then taking the inverse, and that would give us our function of t. And we did that in lab, where we actually did the convolution integral, and then we also did it in the time domain, and we were getting the same answers. And for the simple signals that we're working on, right, that really you might wonder, why do we go into the frequency domain? And that was because we actually do a lot of design or analysis in the frequency domain. And then which is actually very straightforward. So while we were basically iterating constants, ramps, or linear, and maybe in some cases this, right? And we also integrated exponentials, right? It really shines when we start in the frequency domain. We don't have to set up differential equations, right? I can just use voltage division here, right? So we have Vx, V out, and V in, where Vx equals Cc Zr plus Cc, V in. Assume this is an ideal op amp, V out over Vx is just 1, and that's where we can get our transfer function relatively quickly. And it's true that you can, the differential equation for this part right here isn't that hard, right? And since we're saying that's a buffer or a gain stage, whatever you find over here for Vx, you would just multiply it. Again, not that hard. Where it gets hard is even something like this. So this impulse response is this impulse response. And even if it's the same circuit, okay? But to find V out here, right, and find the step response, I would have to find the convolution integral of the step I have to find this, right? And then whatever resulting function I get, this is, which, you know, as we remember, is this, right? Well, in order to find what's going to happen out at the next stage, this becomes my G of t, but then I have to convolve with this next signal, right? So the step gives me V out. Now that V out becomes the G. HT is still the same. And you can see how that's going to be difficult. All right. Where this is really if everything is equal, omega naught. So we have our low pass filter times our second low pass filter. Which gives us this relationship. And we have two poles at minus omega naught, right? And you can take the Bodhi plot of that. And then if you want to go back to the time domain, all right, all right, I want the step response. That's the input of the step. And at this point, there's partial fraction expansion, or the table that I give on exams is from Swarthmore, because I happen to like his table of integrals. Oops. So I usually just cut and paste this and put this into the cheat sheet. Now for this exam, it's open book, open note, open internet, just not open person. Okay, no help from any person or an intelligent chat bot or anything like that. And so you can look here and you'll see there's a repeated pole. There's a step response of a single pole, two poles that are different, step response of two poles that are different. Here we go. Step response of two poles that are different. Now he doesn't have the omega. If I had a squared here, this would just come down to 1 minus e to the minus at. Okay, so this would be the actual thing that we need. Which then I take the inverse Laplace transform of that. We get this. So it, somewhat familiar, right? But we also have this term now. And that turns the plot into so here, if this is just a regular first order, it looks kind of straight and then it rolls off. Okay. Where this it kind of turns on here rather than this kind of straight looking feature here. Okay.
Professor, should there be a 1 over omega naught square in front of the Laplace?
Oh no, it gets canceled out by the omega squared.
No, it's a good question, and you're right. It does get canceled out. Is that notice that's just one where we have omega naught squared. So if I put omega naught squared and then take the inverse, I would have omega naught squared and it cancels out. I'm not quite sure. I mean, if it were me, I would have the table, I would do it like this. I'd have A, right, S plus A squared going to and yeah, it's in the table, but remember, it's all, if you don't put that UT in there, you are going to get really crazy results when you plot. So I'm just reading through. I know I was mentioning the exam. So let's just take a little thing and go over very specifically what is allowed and not allowed, right? So, the lab manual, sure, allowed. Notes, allowed. Yeah, I guess if you want. Videos, it's allowed. Okay, any kind of communication. So I'm sure if you look at the definition of the word communication, right? That's I don't think I have to specify with who, right? You can ask me questions or get clarification and things like that, right? What I don't know is, are there, I mean, Python is big in data science, which means artificial intelligence. And so I'm sure there's chatbots that you can run in Python, right? And if somebody had developed a chatbot to imitate me, right, then, and it was as good as I am, right? Well, that wouldn't be allowed, okay? Now, can you use Python or Ltspice, right? So you can use those to check your work, all right? But what you're going to get is a MyOpenMath exam. Let's take, for example, the question I happen to be working on right now. Not that question. I mean, it could be that question. All right, here's a circuit. We have the resistances and capacitances, and you have to derive the transfer function, right? Which you just enter in, right? And we're going to have a practice with this. Then you draw the magnitude, which, and this is actually what we're going to talk about today as well, right? But the cutoff frequency is a kilohertz. And R3 is 90, R2 is 10, so the gain is 10, so it's 20 dB. So the magnitude is this. Oops. The cutoff frequency is here. It's a single pole, so down 20 dB for every decade. Right? The phase isn't working yet, right? So if the transfer function, the gain is 10, so I would just put 10 times the cutoff frequency divided by S plus the cutoff frequency. Oops. That it's probably going to evaluate right, even though it looks wrong. So even though you don't really have to put parentheses there, if you do, it'll be a little bit easier for you to see. Or you could put the parentheses here. But again, it's just going to evaluate this equation like code. This is just making it look like it's easier to see, right? Again, the phase I don't have working yet. The time domain step response. So the gain was 10. This is a low pass filter, right? No delay, so I have UT times 1 minus EXP. Omega naught was 1,000 times T. All right, so that's the equation for the step response, which then you want to plot. Now notice I have 1, 2, 3, 4, 5. There's a time scale here. So everything is in milliseconds. So I want to plot here at tau equals 1 millisecond. That's like 6 and change. 2 tau is 8.5 and a bit. 3 tau is close to 95% of where you're headed. I see your chat. I'll answer in a question. 4 tau is like 98. 5 tau is, you're practically there. Then you'd submit it. Oh, great, I got that right. Oh, I missed it. Oh, I even got that right. And something happened here. So, even myself, when I do an exam, I have to go back and make sure I've done it right. Okay. But so here's the thing. What if that's right, but I've done it wrong here? Well, the thing is what you're doing is you're doing the work on a piece of paper, right, the whole time, which you'll scan and turn in at the end of the exam. And that way I can go through and check for partial credit. And yeah, I mean, I can tell if something was a typo, right? Let's see. Now, yeah, for me, it'll show the answer. And it looks like the code is wrong. I should have had a multiply sign there. Okay. Which is probably why I got it wrong.
Professor?
So, but anyway, I'll fix that later. There was a chat here. So you have one attempt, okay? This is an exam. You can't keep putting in answers and it's going to tell you whether it's right or wrong, okay? And then you go from there. You get one attempt. But here's the thing. If you're anything like me, you're going to have a typo somewhere, right? And it'll automatically grade. And maybe you'll get it wrong at first. Then I go and review what you actually wrote, and then I can take care of things like that. I would never make it so that in a high stakes exam like this, it would be dependent on something like a typo. So what'll happen is you'll take the exam and you'll be submitting your answers and write, into My Open Math, but you'll be doing them on paper as well, right? Once the exam, so then you take your exam that you did by hand, scan it, or however you, just like homework, put it into a PDF and upload it, right? Once the exam is over, that automatically graded part from My Open Math, you'll see that grade, right? But that's not your final grade. That grade will be, I have to go in and make sure that you, that you did it. If you can't just answer, you just can't put in an answer. And yes, Python and Ltspice are great to check your work, but you can't just submit that code, right? You have to show your thought process, all right? So answers with no justification would be marked 0, okay? So yeah, can we use a digital notepad or an iPad as our scratch paper? You can, but what I found is it's really hard to read. And the digitizer on iPads, you end up drawing things in a very huge way. And I really think it's better to use paper and then take it and then use the Adobe scan to PDF, right? What we're going to do though is on the day before the exam, we're going to have like a mini practice where you do just one problem and then you upload it just to see if the process is working, right? No, so as far as the test, there's a sample exam in the module. You can go and see how many questions and what everything is like, right? But it's 5. It'll keep you busy for most of the whole time, all right? You do not need to activate a My Open Math account. This is all done through Canvas, okay? So again, it could just be some people don't know how to use their iPad, and it's just sometimes they. Matthew, you can't see it, or it's locked or something.
It's coming up as hang on, let me open it again.
Something.
Yeah, when I open it,
Something not helpful. All
dropped
right.
lock on refuse to connect.
Yeah, I mean, hmm, that's weird. Maybe I had the solution done ahead of time, and I didn't want anybody seeing it. But that's midterm. That's midterm. Those are just midterms too. But we're gonna. I'm just gonna fix this.
I can open it, but I have to open it in another tab. That's all, really. Or this is for the 2019. I don't know about the
You know what?
right, the old exam solutions.
All right. I don't know what happened. I called it midterm 2, but this is a midterm 1 solution. Okay. It's there. It seems to me that Canvas is best done with a kind of a PC with a large screen. Then you can see everything. Okay. But yep, that would be a sample. All right. And as you can see, I do my answers in Python, right? Because my handwriting is kind of bad. And so since people will use this to learn from, I kind of do it that way. That way you can read it. Okay. Okay. The you're going to get a chance to do that problem ahead of time, and it is. And if you saw how I did it, right? I mean, you start off here, right? Then I have a certain tau, and I come up by 6. You know, I kind of went like this, and then I said the next tau is about 8.5, and then the next tau is a little bit closer, and then here, right? Now, but here's the thing. If you're getting marked off because the tool is too sensitive, right? That's okay. I'm going to, again, it's the MyOpenMath is there to deliver the exam and partially grade it, but also it gives me an automatic solution that I can see, all right, to help me grade. But plots, right, I have to kind of arbitrate partial credit. Because sometimes, I mean, I don't know if you noticed, right? it's giving me partial credit and I haven't done anything. Well, that's not going to work. So there's things that I have to fix. Excuse me. Okay. But yeah, when it's for as far as sensitivity is concerned, and I'm not right now. I don't really want to fix the midterms. If you can't see those midterms, just send me an email and I'll fix it after class. Okay. Today we have to link the time in the S-plane and go back and forth. We've been doing it, but what happens is we spend time in the time domain, we spend time in the S domain, and then we forget that it's all the same system. We're just looking at it at different ways. All right. So so it's also a review, but also what we're learning is how these things are linked. So we have the step response. So in time, right, that's UT, but in the S domain, right, it's that, okay? So I don't like this. So we're gonna, today, this example is just gonna be low pass, okay? So the input is a step, time, the system, right? Because it's circuits. Okay. So the time domain step response is this. Okay, and again, we can write this in terms of all right. Now, this system doesn't have any gain, right? But we could easily put that in and just multiply everything by a G. Okay. Now, sure, when we do the Bodie plot, it's going to be on a dB scale, but so if this low pass filter has a gain of 10, right, everything gets scaled by 10. All right. Now let's draw the system over here. And I'll use the naming convention that's actually in that question. Okay. So we have a gain stage. Right, it's an ideal op amp configured in a non-inverting stage. What's being fed into that is a low pass filter. And there's our transfer function, which then we can just write this. Now, everything's pretty generic right now, right? So if we set R3 equal to 0, right, we get this. It doesn't mean that we've taken the resistor out of the circuit. What we means is that the resistor is 0, so we kind of get a wire. So the gain is 0 divided by R2, which is 1. All right. So because it's a 1 volt step, right? It doesn't have to be 1 volts, but the output is going to be the gain times 1. In this case, the gain is 1, right? So in order to really tell me what's going on, you have to have the number here. And then this is 5 tau, or 5 divided by omega naught, right? So if omega naught were 1 kiloradian per second, this would be 5 milli, 1, 2, 3, 4. Okay. And so if we look at this, I'm just gonna do the exponential decay part. Right? The bigger omega naught, the faster it decays, and so let's call blue omega naught equals 1 k radian per second. let's call this green color, right? Omega naught less than 1 kiloradians per second. And then this red color, so as the omega naught, the frequency goes less than. As the frequency gets less than this base value, it takes slower to charge. I'm sorry.
Professor, isn't it 5 omega naught as opposed to 5 over omega naught?
So tau, right, is time, and it's 1 over omega naught.
Oh, okay.
So, so in this case, tau would be 1 millisecond. Okay, good question though. But so the bigger omega naught is, right, the faster it decays. The smaller it is, the slower it decays. So yeah, if you notice, if you start looking at things, you can see that omega naught equals okay. I need that space, so I'm going to erase it. All right, so that's the time domain. Now let's look at the frequency. So it's a low pass filter with a cutoff frequency of 1000. I believe we set the gain equal to 1, so that's going to be 0 dB. We have 1 kilo ohm radian per second. And then it's first order, there's only one pole, right? So minus 20 dB per decade. What did I say? Let's just say omega naught equals 1 over R1C1. Tau equals R1C1. Okay? The phase right? It's a first order low pass filter. So we're gonna, the points that we want to plot are 0, minus 45, and 90, right? At omega naught, we're going to be at 45. Omega naught divided by 10, we're going to be 0. And above omega naught times 10, we're going to be 90. All right. So the blue line here is the time, and this is the frequency, and they represent the same signal. Now, if omega naught is greater than 1000, that means in the frequency domain, right, it's going to be out here. And then the phase gets shifted here. For omega naught less than 1,000, it's going to be something down here. And then the phase does something like that. That's great. It's good that you're helping each other out. Sometimes you can see what you need better than I can. Now, yeah, on this plot, that's the cutoff frequency, but then it's not perfectly on the same scale, all right? It's just a sketch. All right. So here's the thing is that the input, right? It's a step edge, right? In the frequency domain, that's 1 over S, right? So it's going like that. Now the magnitude might be going down with frequency, but there's a lot of frequencies there due to this edge, all right? And a low pass filter, right, will pass some things and start to attenuate others. And so if that edge is a lot of frequencies, right, and it smooths out that edge, right, that means we're getting rid of higher frequencies, all right? If you're letting more of that edge in, that means you're passing more frequencies. So it's going to look like that, right? If you are letting less frequencies in, that means you're going to round that edge more and more and more. And let me just label this magnitude and omega. I don't, for this part of the discussion, I don't really need to see the phase, right? Here's a cutoff frequency, omega 1, omega 2, omega 3, omega 1 is less than omega 2 is less than omega 3. And notice how it's letting more of that edge in. Okay. And that's why we call it, so it's rounding that edge, and that's why we call it a low pass filter. All right. Okay, it looks like you answered that question. Great. So now, all right, I recognize that this is a high pass filter. When omega is a lot less than omega naught, S is going to dominate, and I'm going to have an upward slope. Then at some point, this will be bigger than that. Omega will be bigger than omega naught, and then the S's will cancel, and it'll flatten out, right? So this is just magnitude. And then for the phase, if omega is a lot less than this, we're left with S only, which is J omega. So that's 90, 45, and 0. Okay, and that's the phase. Now this is HT equals. That's a delta function minus a decaying exponential, delta function minus decaying exponential. Okay. So we'll say 1K radian per second. All right, well, what if omega naught is less than 1K? Well, it's going to shift this whole curve over by some amount. Okay. Okay, the phase is shifted. What about omega naught greater than 1 kilo ohm? Radian per second. Pushes the curve that way. Phase gets moved back and forth. So what is the step response, right? It's 1 over S times S plus omega naught. Those cancel. All right, you get UT e to the minus omega naught t. So we have that decaying exponential, and at t equals 0, right, you get that function just becomes 1. So let's call that 0. Okay. So in this case, the frequency omega naught is a lot less than I mean, omega naught is just less than 1 kilo ohm. 1 kilo. So it's actually going to go slower, right? If omega naught is smaller, it decays, takes more time to decay, right? And then this yellow omega naught is bigger than 1K, so it'll decay faster. All right. And what this is doing is detecting the edge, right? Because if I go from 0 to 1, I know that there was an edge to the signal, all right, that it just found. And all I need is I'll draw it bigger. If I have a comparator, if that's at 0.5 volts, and then this is my output of this signal here, right? As soon as I go above, I know that this will be bigger than that, and I'll just get a pulse out and that, hey, there was an edge there, okay? And then it takes time to decay. So why does this decay faster? Well, if you look, you could think of it as it's getting rid of more frequencies or more energy at frequencies down here. So there's less to kind of get rid of, so if you will, so it decays faster. Here, you're letting more of the signal in, right, to begin with. So there's more that needs to be decayed. And sure, if you push this here, right, it would decay so slowly that it would almost look like a step because you'd be passing everything. And then as this goes forward, it would decay faster and faster and faster to where it was almost like a delta function. Okay. And so on the, exam questions, yeah, there'll be things on you'll see something like that. Is it a low or a high pass filter, right? Let's call that A and that B. And let's say these are roughly drawn to scale, where this is decaying a lot faster than this, right? I can put 0 here and say, all right, the gains are all 1, right? 0 dB. And that here, this cutoff frequency is bigger than this cutoff frequency. This cutoff frequency is bigger than this one. And then, match, right? Well, this is a low pass feature. That's a low pass feature. This is low, and that's low. All right, now which one goes to which? Well, this one decays faster. Its omega naught must be bigger, right? So that one goes there, and that one goes there. And these have, you know, kind of a theme, right? I could give all four, and then you have to match all four, right? There could be what if, you know, if I move this, what happens to this? Right, so if I move that, right, this will get shorter. Right. If I move it that way, it'll take longer. So let's say this is a signal, right? This is, it's a low pass impulse response. This is the low pass transfer function. But notice, right, it takes 5 tau to decay, right? And I'm saying, all right, convolve these functions. Well, you could, I think this was a homework, right? But it's like you have RT minus 1, right? Because this goes up by a slope of 1, then you even it. Goes up by slope, and then go down by 2, flatten, go down by 1, flatten, right? All you need to do is find one ramp to this and then go from there. But if we just want to sketch it intuitively before we get into that math, we know that the resulting waveform, right? Let's just call that T1 and T2, right? This is non-zero for T1 time. This is non-zero for T2 time. It's going to stay on for T1 plus T2. Now look at how wide this is compared to this. And it's a low pass filter. Low pass filters take the edges off of things. Well, that's kind of an edge, 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 right? And even here, it's an even slope, right? The Laplace of t is 1 over s squared, right? So you're filtering, even the slopes have a frequency, right? Well, you know that you're going to start here at 0, you're going to end here, and then it's just going to smooth things out, right? That's a little more to scale. So it delays it and smooths it. Okay. It's, I mean, for a hand-drawn figure, you know, that's okay. Right? But it's blurring those edges, right? But now, so what if omega naught is such that it's a lot smaller than even it's smaller than 100th of this, so that I'm getting something like so sharp that I can't even draw it, right? And let's just say the area is 1. Well, that means this, right, is letting in all the frequencies, and it'll almost look like the original function, because this shape, when omega naught is really big compared to the overall length, is making it look like a delta function. And yeah, if 1 over omega naught is bigger than T1, you know, times 100, well then now T1 plus T2 is, you know, out here, and it just smears the whole thing out. You don't see anything at all because it's blocking so much, right? And if this, and one could do this for a high pass filter as well. High pass filters are edge detectors, but they're slope detectors. And so really an ideal slope detector, a perfect slope detector, no slope, oops, no slope. Then there's a constant slope positive, right? You need a little bit of time. Then the slope goes back to 0. Then the slope, oops. The slope is constant for that amount of time, right? Then it's back to 0. Then it's constant again for a certain amount of time, but then it's negative, back to 0, negative, back to 0. So that would be more a low pass, such that it's only detecting edges and rejects all DC. Food for thought. If there's any questions, why don't you ask me now? While I have everybody, you know, I don't mind helping people with their circuits and their Python code, but you know, email me your code, your Python code, so I can read it in to Spider. That way, all the formatting is there, and it would be a lot easier for me to check. Same with Ltspice. Send me your .asc file, because then I can open it up and see what's going on. Sometimes with a screenshot, there's just, you can't see it. You can't see the issue. You have to simulate it, and then I can find out what's going on. Okay? Whatever it says on the schedule, yep, that's when the review will be. But today was a review. In a way, today was a review. Or the beginning of the review. All right, guys, I'm going to take off and I'll post the video when it gets processed. All right, take care.